Thank you all for coming. So the question I want to think about today is if I have a reductive group G over ZP, and so the sort of main things I'm interested in would be GLN, GSP2N, or GON. And if I have a continuous representation rho bar of the absolute Galois group of Q to the FQ points of this group, the question is, does there exist a geometric lift to characteristic 0? So by a geometric lift, I mean a representation which is geometric in the sense of the Fontaine-Mazur conjecture. So it's ramified at finitely many primes and de Rham at P. And when I'm thinking about this question, I didn't specify exactly what's the bit vectors of FQ. So I could, for example, extend this field. I don't care. I just want some characteristic 0 lift which is geometric. So for the group GL2, this question was by Ramakrishna in the late 1990s. What he showed is if I have a residual representation of the absolute Galois group of Q into GL2 FQ, and it's odd, irreducible, and it also satisfies some technical conditions, he proved there exists a geometric lift. And furthermore, it is actually crystalline at P. So the reason he was interested in this question is because it's connected to the Fontaine-Mazur conjecture and Serre's conjecture. Serre's conjecture, which says that if you have an odd irreducible representation, like this one, it should be modular. And given this result, the Fontaine-Mazur says, because it's geometric, it'll actually be modular also. So this was before Serre's conjecture was proven, so this was seen as a good piece of evidence for Serre's conjecture. And OK. So today I'm going to sort of talk about how you can generalize this technique. So it's already, people have studied it in other contexts. Sort of two notable examples are, in the course of doing many other things, Closel and Harris and Taylor sort of generalized the technique to the group they called GN, which is related to GLN. It's sort of GLN times GL1, and then it's a semi-direct product with a two-element group. And they're able to prove a sort of similar lifting theorem. And Stefan Petrikis has also been interested in these sort of lifting questions, and he's pardon? The non-trivial element acts trivially here, and it acts as the transpose inverse in here. So later, we'll talk about what it means to be odd in greater generality, and this is something where that's possible, and it's not possible for GLN. Right, so Stefan Petrikis also has sort of thought about this, and he's mainly interested in exceptional groups, and he was able to get a version of this technique to work, so he could produce representations valued in the exceptional groups which are geometric, which was very interesting. My work is sort of more closely connected to the original motivation of the sort of generalizations of Serre's conjecture and the Fontaine-Mazur conjecture. So I studied the symplectic and orthogonal groups where the sort of generalizations of Serre's conjecture, which have been being developed, suggest, again, we should be able to get these geometric lifts, and they should actually lift to characteristic 0. So my result is the following. So suppose G equals GSP2n, or GON, and I have a residual representation, rho bar, and the absolute Galois group of Q to the FQ points of G. And suppose it has big image in the sense that the image contains the FP points of the derived group. And suppose rho bar is odd. I'll tell you exactly what that means in this context in a second. Suppose it's Fontaine-Mazur at P with distinct weights in the range 0 to P minus 2. Then I show there exists a geometric lift that is Fontaine-Mazur at P. Okay, so in this setting odd means that if I take tau equal the image of complex conjugation and view it as a involution of the Lie algebra, the fixed points are equal to the number of roots of G divided by 2. So Cartan proved that it's always at least this big, and this is saying it's as small as possible. Okay, so some comments about this theorem. So
functoriality preserves oddness as you go through different situations? I mean, I assume it does, so that you never change from an odd to an even.
Yeah, I don't think you should be able to. Okay. So there's some sort of hidden assumptions in here. Let me sort of spell them out. The first one is, in contrast with Ramakrishna's result, we don't see the word irreducible, but that's sort of implied by this big image assumption. Also, it's the assumption that P is not too small, because there have to be these distinct sort of weights, which are the jumps in the Fontaine-Mazur filtration. So this is saying, because they're distinct, P is not too small. Just also worth pointing out, being the Fontaine-Mazur at P implies it's crystalline. Okay. So I want to sort of set up some notation so I can sort of describe how Ramakrishna's idea for GL2 generalizes, and then talk about sort of the sort of heart of the matter, which is actually the analysis of local deformation rings at primes which are not P.
What actually is the Lie algebra of G fixed by C?
Yeah. Yeah, so it's the image of complex conjugation acts on the Lie algebra by the adjoint action, and what are the fixed points?
The fixed point?
It's the, sorry,
Linear subspace. Or dimension.
Yeah. Okay. Okay, so suppose S is a finite set of places. Of Q, and I want P and infinity to definitely be an S. And so gamma S is the Galois group of the maximal extension of Q, which is ramified only at places in S. And gamma sub L is the local Galois group sitting inside gamma sub S for L and S. Okay. And now rho bar is our residual representation. It's unramified outside S, so it factors through here, say. And K is just some finite field with characteristic P. And O is going to be the unit vectors of K. So the hope would be just produce rho sub n from gamma S to the O mod P to the n points of G that satisfy the Fontaine-Mazur condition of P, and then just sort of lift these and then put them together into an inverse limit. So it's not going to be quite that simple. We're going to have to extend the set S and sort of be more careful about the local behavior. So I'm going to need to have a set of deformation conditions for places in S, call them D sub V. And suppose that L sub V is the tangent space of the one at V inside the tangent space for the deformation functor. Okay. This is the adjoint representation. So, okay. So examples of these are an unramified deformation condition, or if your residual representation was just tamely ramified, say it stays tamely ramified. Okay. And then so the key idea of Ramakrishna's argument and its generalizations is if a sort of generalized Selmer group which is the set of X in the H1 of gamma S with coefficients in ad rho bar, such that the restriction at all the places in S is in LV perp. So if this equals 0, then a sort of local to global principle holds. And this perp is the sort of annihilator under Tate duality. Okay, so the sort of principle is you can deform rho n to rho n plus 1 subject to this deformation condition for each place in S. Being able to do that is equivalent to being able to deform a bunch of local representations. Just the restrictions subject to the same deformation conditions.
Twist by one somewhere.
Yes, I do. So, sorry. Yeah, so this is a sort of dual, and in the sense that it's isomorphic to the just Tate twisting. Yes. Okay. Okay. So Ramakrishna's idea, which you can make work in general, is we're going to enlarge S and sort of allow rho n to ramify, but in a sort of in a controlled way at some new places. And so you can work out, there's a way to sort of control the size of this dual Selmer group. Via sort of a resulting a product formula in Galois cohomology, we usually interpret it to Wiles. And you get some expression, and in that expression there is a term which is H0 of the absolute Galois of the Galois group of C over R. And in order to get this method to work, you need it to be as small as possible. And that's exactly the condition that rho bar is odd. Okay. So this is the sort of place where if you tried to do this for GLN, you wouldn't get it to work. You wouldn't be able to kill this obstruction to this local global principle. And that's good because, as far as I understand, there's no reason to expect that sort of just a random Galois representation for GLN is actually going to lift. Okay. So, given this principle, our goal is we just need to set up local deformation conditions so that we can always lift locally. And the way to do that is to show that the local deformation ring is smooth. So L equals P is one of the cases. I'm not going to say much about it. I'll just say you can sort of take Fontaine-Mazur theory, which gives you such a nice such deformation condition for GLN, and then sort of modify it to work with a pairing. Nothing. I think that's all I'm going to say. But how about for the other primes, L not equal P? Well, again, for GLN, this has been studied in this paper of Closell, Harris, and Taylor. So the first step is to reduce to deforming representations of a much simpler group. So representations, say, rho bar of groups T sub L. And then where T of L is the following. You sort of look at the tamely ramified Galois group. We know this is just a semi-direct product of Z hat and a copy of Z hat, except we removed all of the we removed the prime L. And we can sort of take a quotient, which is what I'm calling T sub L, which is just Z hat semi-direct product ZP. And so let me write down the relation of the semi-direct product. So if phi is the Frobenius, which generates the Z hat, and the generator of this part is tau, the relation is that phi inverse equals tau to the L. Okay, and the continuity condition forces that rho bar of tau is unipotent. In particular, rho bar of tau minus identity is nilpotent. So to study this, Closell, Harris, and Taylor defined the following deformation condition. They said a lift rho TL to GLNR is minimally ramified if the following condition holds. So you sort of look at kernels of tau minus the identity and look at the kernel of powers of this. And then you get a natural map to the same sort of kernels for the residual representation. And the condition to be minimally ramified is this is an isomorphism for all I. So you should think that these elements are sort of how bad the ramification is, and this is saying, yes, the residual value was ramified, but when I'm lifting, it's worse in some sense. Okay. So that works great for GLN. If I want to do this for some other group, I would sort of like a more group theoretic reinterpretation of this, so I can have a hope of analyzing it. So a natural but wrong idea is to say, well, these kernels give me a flag. Flags are the same as a parabolic in GLN. So I could try requiring that rho of tau lies in the unipotent radical of some, the R points of the unipotent radical of some parabolic that lifts the residual parabolic. And it's a consequence of the relation that implies that the image of phi is also in the R points of this parabolic. Okay. However, if you try to do this for, say, a symplectic group, there's a problem. Because parabolics in GSP2n, they correspond to isotropic flags. Which are flags where the first is the complement of the last piece, and so forth. And there's no reason to expect this sort of flag here is actually isotropic. You could be bold and say, well, maybe I can modify this flag somehow, or just pick some parabolic, which is like a refinement in some sense, and then get it to work. Unfortunately, I found an explicit example with GSP4 F7. That is, if you sort of formulate a deformation condition along these lines, it's not smooth for any choice of parabolic. Okay, so
Is 7 important?
no. So assuming I have time at the end, I will sort of explain why this is a general phenomena, and it's not specific to this group or the field. Okay. So a better idea is, very roughly stated, is that rho of tau should have the same unipotent structure as the residual image of tau. Okay, so I'm going to make that more precise. So actually, the first thing to do is, because p is large, I'm going to use the log and exponential for unipotence to convert this into a question. Instead of about, say, rho bar of tau, I'm going to convert it into a nilpotent n. This is in the k points of the Lie algebra. And then if you do that, the relation is now that when you conjugate by rho of phi, you get L times n bar. Okay, this is sort of partly just due to the fact that people have studied nilpotent elements and have better references than for unipotent elements. Okay. So over an algebraically closed field, nilpotent orbits, which are the orbits under the adjoint action of the nilpotent elements in the Lie algebra, they can be described by partitions. This is essentially just specifying the Jordan canonical form. So for example, for GSP4, it's partitions of 4 such that the odd numbers appear an even number of times. Okay. So let me sort of give you a couple examples of this. So maybe you have the partition 2 plus 1 plus 1. That corresponds to sort of giving this Jordan block structure. And partition 2 plus 2 corresponds to different structure. Okay. And there's some more partitions and more examples. So this is over a field. Now I want to sort of talk about the situation over the DVR-O. So for a nilpotent, or for some element in the O points of the Lie algebra, we sort of want it to look the same. We want the same partition for the sort of image in the special and generic fiber. And so this would rule out something like this matrix, where it reduces to this one, but over in characteristic 0 over a field that's conjugate to this one. And so, sort of motivated by this example, we can define a notion I'm calling pure nilpotence of types sigma, let's say we're in some partition, over a general ring R. And the reason I chose pure is because it's sort of saying this condition that the special and generic fibers are sort of the same in some sense, at least when you're actually over it. O, as opposed to just something like Z mod P to the N. So I'll come back and give you an actual definition of this, but assuming we have this notion, we can now define a deformation condition. So a representation of the group TL, which I'll remind you is just the semi-direct product of Z hat and ZP. So representation into the R points of G is minimally ramified. If rho of tau is the exponential of a pure nilpotent. Over R. Okay, so because we're a lift of some residual representation, the sort of type of the nilpotent is already fixed by what's happening over the residue field. And this is just saying the minimally ramified deformations are the ones such that when we deform to like z mod p to the n, it still looks like we had the same nilpotent shape and we're not deforming towards something like this. Okay. Okay. And then the result I prove about this is the framed minimally ramified deformation ring is formally smooth over O. Okay, and this is what lets you then use Ramakrishna's Ramakrishna's local Galois principle and actually get the geometric deformation. If you didn't have this sort of result, you would have to either hope you're not ramified to any other primes besides p, or you can define sort of more special deformation conditions which work. But this one is more general. Okay. So the sort of idea of how to prove this is I'm going to actually tell you what being a pure nilpotent of some type means. And then we're going to then pick the image of tau to be the exponential of a pure nilpotent, analyze that space, and then finally pick the image of the Frobenius. Yeah?
So in your global result, you have to have some assumption excluding ramification at small primes or something, given you seem to be assuming that P was large here.
Yeah, so P is large. That's the characteristic of the field over which I'm doing the resorption. So it's like a representation over a field of characteristic P, but I don't care about L here. Yeah. Yeah. Okay. So because I can assume that P is large enough, we have versions of the Jacobson-Morozov theorem. Over the finite fields. And what they say is that n bar is this nilpotent, is a raising operator in an SL2 triple. So what does that mean? It means we sort of have a nice sort of picture of how n acts. So maybe if my type is 3 plus 3 plus 2 plus 1 plus 1 for GSP 10, okay, it means there's sort of a basis where n bar acts like this. Okay, so we have these strands where n is raising it up. We have these lowest weight vectors. There's also the data of a pairing, which sort of pairs between these two strands and pairs within the strands with an even number of things. And so there's sort of the data here, the grading. And it completely depends on just the partition. And then we have sort of how one level fits into the next level. Okay. And so this is the picture that we're going to sort of think about to define pure nilpotents. Okay. So a definition is an element in the R points of the Lie algebra, and sitting inside, using the standard representation, so it's acting on some space M sub R, which is a free R module. So we say it's pure of type sigma if there exists a basis of MR such that n acts sort of as this recipe predicts. So to actually write it out, it's a sort of complicated condition involving a lot of notation, but I hope you can sort of see what the picture is supposed to be. And so if R was now just the characteristic 0 dVr O, the fact that there exists this sort of integral basis means that in the special and generic fiber, it actually does have the same behavior. Okay. I guess sort of philosophically, this is sort of the same idea as you use in Fontaine-Mazur theory, where you define something over like z mod p to the n with a lot of sort of data, and then in characteristic 0, that recovers a condition that you like being crystalline. Okay. There are various sort of there. So I think I only know about Jacobs the Morse over a field. So like this is the picture over a field.
Oh, that's the picture of the field.
Yeah.
Yeah.
Yeah. Yeah. And exactly.
But even as long as you're on characteristic for a symplectic over a field, it's determined by a certain form.
Yes. You can.
So you can still sort of do it.
Yeah. In terms of exposition, the Jacobs and Morse is like the way to see it. But the place I learned this stuff about nilpotents is from Jansen's book, and he builds this sort of picture directly in any characteristic besides 2.
Right.
But okay. So we have a definition. Let's analyze it now. So I'm going to show this smoothness. So I want to sort of think about just right now, just pure nilpotents of some type. And I want to sort of now just think about pure nilpotents, just gratings of type sigma for O. Okay. So the first step is to analyze this. It's smooth essentially because the smoothness of flag schemes. Once you figure out like this grading, and then maybe I need to actually be a little more precise and keep track of where the image of the lower weight things was inside one step. Once you keep track of all of that, it's just some sort of flag, and then you're like, okay, I know it's smooth. And even better, sort of over it, the universal grading is G conjugate to the sort of standard grading you would get if you just sort of pick your Jordan canonical form. Okay. And then now that we've sort of picked a grading, we just want to pick a nilpotent. And because of this being the universal grading is this conjugate, we actually can just calculate with our standard, our favorite grading. And then we see that the sort of set of nilpotents for that grading are just things which map one level into the next, and as an isomorphism. And then that you can just directly inspect that, and yet this is also smooth. And then again, the universal nilpotent over here is then conjugate to a sort of standard nilpotent. Okay, so nothing too deep going on here, just a lot of bookkeeping. So now I want to think about the actual deformation condition, so I need to pick an image for Frobenius. So I want to consider pairs of matrices, phi and n, such that phi is in the R points of G, n is a pure nilpotent of some type, and that satisfy the correct relation. Okay. And I want to think about it now over just the pure nilpotents of the same type. Okay, and I claim this is smooth. So because the universal nilpotent over this is just conjugate to a standard nilpotent, we actually just need to consider the fiber. Okay, and then by inspection, we can actually find one phi which works. It's a sort of diagonal matrix with different powers of L on the diagonal according to the block structure. So maybe it looks something like this. We have a block of size 3, and then it starts over in each block, okay? And then you can just check that that works. So the fiber then is just the centralizer of n, standard, times this particular lift. So to understand this space, I just have to understand this centralizer. Now, the good news is this is something which has been studied. The bad news is it's only studied over fields. So the idea is we're going to leverage that case. Okay, so there's sort of a technical lemma in algebraic geometry is going to help us out. It says if I have a morphism x to spec of O, that's of finite type, it's flat provided the following conditions start to hold. First of all, the fibers are reduced. Secondly, the dimension of the special and generic fibers are the same. And thirdly, there exist sections to f, x sub I, such that all irreducible components C of a fiber, for each one, there exists some section that meets that fiber only in C. Okay. So there's a picture for this. So the picture is, I have some components in the special fiber, I have some components in the generic fiber, and I have these sections. Okay. So this lemma is not too hard. Sort of the idea is you take the closure of the generic fiber. We know this closure is flat. And then we're going to show that the closure is all of x. The sections show us that it actually does meet all of the irreducible components of the special fiber. And then we use the fact that they have the same dimension and the fact that the fibers are reduced to show that's actually everything. OK. So if you want to apply this to deduce smoothness of the centralizer, well, 1, that's just the classical smoothness over a field. The second one, this holds because n is pure. Right, so the only reason we would expect that the special and generic fiber have the same dimension is exactly because we've rigged it that way. And for the third one, well, it's a little bit of work. You sort of think about the connected components over fields. And they sort of have some points which look like they should be integral. They're just written down in terms of like zeros, ones, and negative ones. So what you do is you sort of mimic the analysis over fields in order to show that, yes, in fact, those points actually do lie in this scheme. And those gives us the sections. OK? And so together, this gives that this space is smooth over O. And that lets us analyze the deformation condition. OK? So I should just remark, you could also run this with GLN. And it gives the same deformation condition, but it gives a different perspective. Sort of doesn't involve quite as much explicit building of the deformation ring. That's thinking about matrices. OK. So the last thing I want to talk about is what I promised earlier, which is, so what was going on with that example I found? So it was an example with GSP4, but once I explain what's going on, you'll see it's not specific to this group. So over a field, if I give you a parabolic, there's a sort of standard way to associate a nilpotent orbit to it. It's called the Richardson orbit. And what it is you sort of look at the Lie algebra of the unipotent radical of P. And one nilpotent orbit has a dense open intersection. And that's the Richardson orbit. OK. So now let's think about what are the parabolics in GSP4. Well, they correspond to isotropic flags. So besides the very boring flags, we have a sort of flag which jumps by 2 each time, and we have flag which jumps by 1 each time. And if you take these parabolics and apply this the associated Richardson orbits are the orbits that correspond to the partitions 2 plus 2 and 4. But this is all the parabolics, but there are more partitions. For example, 2 plus 1 plus 1. So if you look at maybe this parabolic, there's sort of a big piece of it, of the Lie algebra, is this 2 plus 2 orbit. And then there's some other piece which is coming from these other partitions. Okay. So if you try to define the deformation condition based simply that rho of the inertia lies in some parabolic, and your residual guy was in this smaller piece, you can deform into something which is sort of a mix of two of these and is not pure. So that's sort of explaining why this smoothness doesn't happen. But for GLN, every nilpotent orbit is a Richardson orbit. What it means is when you sort of try a deformation condition based on parabolics, you can always arrange to start off in the sort of big piece, and then whenever you deform, you're not going to sort of change the nilpotent type, and therefore you will exactly be recovering the deformation condition from Closel-Harris-Taylor, but if you try to use pure nilpotents, it's the same thing. All right, so thank you.